Theory. This experiment studied the reaction kinetics of a simple homogeneous liquid phase system between isopropyl acetate and sodium hydroxide, which is an example of saponification. Kinetics is the study of how fast or slow the concentrations of reagents change during a chemical reaction and the factors that interfere with this speed. A batch experiment was first implemented to monitor the conversion over certain time intervals. From this data, a rate constant and activation energy can be determined at several temperatures using the rate equation for an irreversible reaction. A batch reaction is oftentimes used for small-scale productions because the reaction cannot be modified while it is running. The advantage of this is that there is a high conversion per unit of volume and can produce a variety of products. Batch reactors are easy to clean but have high operating costs as compared to a continuously stirred tank reactor, or CSTR. Unlike a batch reactor, a CSTR has a continuous flow of reactants and products through a vessel. This type of reactor is run to steady state where the outlet is at the same conditions as inside the reactor. CSTRs are used when agitation is required and can be assumed to be perfectly mixed. The advantage of using a CSTR is that it has good operational control over the system's flow rate and temperature, and unlike the batch, it has a low operating cost. A batch reaction is a process where two or more species are placed in a container at specific condition and a reaction occurs. Throughout the reaction, no new species are introduced and no products are taken out. The reaction runs to completion and then the products are analyzed. The experimental batch reactor analysis of the rate constant at several temperatures can be used to design and size an appropriate CSTR. The effective temperature on the rate constant can be determined using the Arrhenius expression. Rate data at the various temperatures can be used to determine the frequency factor and activation energy. The CSTR found in lab was then used to obtain experimental results and then compared to our predictive model. Experiment. There are two parts to this experiment: batch reactor and CSTR. In the first part of the experiment, the kinetics such as the rate constant and activation energy of the reaction will be determined. Initially prepare and label the following reagents: 1 liter 0.1 molar sodium hydroxide, 0.1 molar hydrochloric acid, and 0.1 molar isopropyl acetate solutions in volumetric flasks. Place 5 milliliters of hydrochloric acid in 3 separate Erlenmeyer flasks. Next, set the temperature of the heater to the appropriate temperature. Place the reagents and set the timer for 10 minutes. Erlenmeyer flask, where the reagents were mixed, to a flask containing the hydrochloric acid. In order to obtain accurate data, pipette 3 samples at 1, 3, 5, and 7 minutes after mixing the reagents. Once the sample is pipetted at the designated time intervals, quickly titrate the sample with 0.1 molar sodium hydroxide solution. Repeat the process for 3, 5, and 7 minutes of time interval and record the volume of titration needed. Subsequently, graph the data and the calculation results in MATLAB in order to obtain the necessary data to obtain the rate constant for the CSTR experiment. After carefully obtaining the necessary data from the batch experiment, prepare fresh reagents in order to run the CSTR. Before running the experiment, first calibrate the volumetric flow rates of the pumps. This can be done by running the pumps at different speeds and obtaining a sample for a specified time. Next, set the temperature of the heater to the appropriate temperature, just like in the batch reaction, and fill both tanks sufficiently with fresh reagents so that no air will be let in the pumps. Turn on the caustic and ester pumps to allow the draining tank to fill. Once the tank has reached 1 liter, turn on the outlet pump so that the volume stays constant. Start the timer and wait 2 residence times. Take out some products to a waste container before obtaining a sample of the reagent. Pipette 3 10 milliliters of product into 3 flasks containing 5 milliliters of hydrochloric acid solution. Titrate each sample with 0.1 molar sodium hydroxide solution and record the volume. safety. There are 3 controls: administrative control, engineering control, and personal protective equipment. To prevent contact and ensure safety, all technicians handling the reagents or taking samples from the reactors should wear gloves, eye goggles, and a lab coat at all times. Isopropyl acetate is also flammable, hence should be kept away from any source of heat. If more ester is necessary, have an experienced lab technician mix additional solution in a well-ventilated area to keep the concentration of vapors below their threshold limit. The setup of the CSTR experiment involves the use of 3 pumps: caustic, ester, and outlet pumps. It is vital that the pump reservoirs be filled sufficiently above the outlet prior to turning the pumps on to avoid any air in the pumps. Pumping air through the pumps can cause damage to the seals, and after a prolonged time, the pumps will stop working altogether. To prevent any damage to the system, keep watch on the levels of the caustic and ester tanks and try to keep them above 3 liters throughout the experiment, even when flushing the system. The outlet pump controls the draining tank and should not be running if the level of the tank is below 250 milliliters to ensure no air is let in. Results. This plot gives us the linear correlation of the flow meter and the actual volumetric flow. These plots show the concentration of sodium hydroxide as a function of time. According to the literature data, the saponification reaction is second order. The experimental data was compared with the theoretical data by using the reaction rate constant found in literature. The steady-state time of the CSTR was obtained by the mass balance equation. As you can see, it will take shorter time to reach steady state at longer residence times. We compared the reaction kinetics from the batch experiment and the CSTR experiment. The experimental data was compared with the theoretical data by using the reaction rate constant found in literature. The conversion was obtained from the experimental data and the design equation of a CSTR. The discrepancy was caused by experimental and operational error. Conclusion. We can conclude that the saponification reaction is second order. As shown in the graphs, it will take less time to reach steady state at longer residence times. The discrepancy was caused by experimental and operational error. Further studies need to be done in order to improve the accuracy of the data presented.